The word polar has its roots in like the Earth having poles. It basically means something that has two different ends. In the case of the Earth, the two different ends are the North Pole and the South Pole. In the world of chemistry, when we talk about poles, the two different ends are the positive end and the negative end. So when we talk about having a polar molecule, what we're really saying is that our molecule is in some way lopsided. So we're looking at a lopsided molecule with an asymmetric distribution of charge. Or in other words, a molecule that has ends. And in order to decide if the molecule is going to be polar or nonpolar, we are going to need every skill that we've learned today, the class before this one, and the class before that. Because the first step is to draw a Lewis structure, and we handled that 2 classes ago. And then you have to know if there's polar bonds or not, and we just handled that today. And then you have to know the molecular shape, which is what we did in our last class. And then you've got to put the positives and negatives in, and we learned to do that today. And then the last piece of this is you have to look at the molecule and decide, does it have ends? Essentially, can you cut the positive from the negative in one straight slice, in which case it does have ends, and it's going to be a polar molecule. So we're going to do a few examples together, and then I'm going to turn you loose to do a little bit of practice with this. So our first molecule here is going to be Cl2. Cl2, with each carbon having 7 valence electrons, has a total of 14 valence electrons. It's got a relatively simple Lewis structure. That looks like that. So then we need to decide, do we have any polar bonds? No, we don't, because chlorine has the same electronegativity as chlorine, which means that we basically are done. If all the bonds are nonpolar, stop here, molecule is nonpolar. So we don't even need that one. If we build a quick chlorine, chlorine is the green one in your box. So if we build a Cl2, it's pretty easy to see that the Cl2 is a molecule that doesn't have ends. It's the same looking at it from both directions, and that's what it means to be nonpolar. It means to essentially be the same looking from both directions. By contrast, HCl, with its 8 valence electrons, is a molecule that's going to have ends. The two sides of the molecule don't look the same. If I check on the electronegativity difference between hydrogen and chlorine, I find out that that difference is large enough that this is going to be a polar bond. So it has polar bonds. So now I need to think about the molecular shape of this thing, but I don't need to think very hard, because if all I have is 2 atoms, those 2 atoms are going to be a line. Chlorine is more electronegative than hydrogen. So the chlorine is the negative end of the molecule, and the hydrogen is the positive end. And when I build the HCl molecule, I can see that this molecule definitely has ends. It has a negative end of the molecule on the chlorine side and a positive end of the molecule on the hydrogen side. And one of the tests we're going to do for this is to try to make one straight slice that will cut the positives from the negatives. So if I come down like this, I could cut the positive away from the negative. The other way to look at it is, if you pick up the molecule, can you put all the positives toward you and all the negatives the other way? And I can't. I can point the hydrogen at me, which causes the chlorine, which is negative, to point away from me. So all of those things are evidence that my molecule has sides and that the molecule is going to be polar. So it's a molecule that has ends. Next one, CH4. Carbon has 4 valence electrons, plus 4 hydrogens with 1 valence electron each. We're working again with 8 valence electrons. Because hydrogen needs to be at the end of the molecule, that forces us to put hydrogen or put carbon in the middle. And then I have to decide whether I have polar bonds or not. When I look at the electronegativity on hydrogen and carbon on my periodic table, I find out that the difference there is only 0.35. No, that's not going to have any polar bonds, and that's kind of the best case scenario. If all bonds are nonpolar, stop here. Don't have to do this. The molecule is going to be nonpolar because all of the bonds are nonpolar. You can't get a positive and a negative end on a molecule if the bonds themselves aren't causing an asymmetric distribution of that charge. NH3. Nitrogen has 5 valence electrons, plus I've got 3 hydrogens at 1 valence electron each. We've got another situation with 8 valence electrons. I'll put my nitrogen in the middle, my hydrogens around the outside. I have electrons left over, and when that's the case, they go on the middle. Now I check my nitrogen and hydrogen for polarity. So I've got 2.20 compared to 3.04. Yep, that's a big enough difference to make those end up being polar bonds. So now we have to keep going on the list. Draw and name the molecular shape. So the way we manage molecular shape was we started by drawing the electron structure. This has 4 electron positions, which means I need to draw my tetrahedron. The nitrogen goes in the middle of my tetrahedron because the electron structure has to be based on the 4 electron positions idea. Then I'm going to put atoms in the position where there are atoms. So there's a hydrogen here, a hydrogen here, and a hydrogen here. And once we've done that, we erase for where the lone pairs are, and I end up with a 3-dimensional picture of my molecule. So this is a trig pyramid. Now I put in my partial positives and my partial negatives. As I look at the electronegativity, the nitrogen is more electronegative than the hydrogen. So my partial negative goes on the nitrogen. My partial positive goes on the hydrogen. So I have 3 hydrogens that are a little bit positive, a nitrogen that's a little bit negative. So let's build ourselves a model. Nitrogen is blue, and I want you to build this with the longer stick bonds. So some of these bonds are a little longer than others. Just to exaggerate the size, use the big bonds to build your NH3. And our model kit confirms for us the trigonal pyramidal situation, because I can slide something underneath here. We can see that the blue one isn't touching the table. Now I'm going to pick this thing up and I'm going to look at it, and I know that the nitrogen is negative and the 3 hydrogens are positive. I can flip this thing to point all 3 hydrogens at me, so I can put all the positive toward myself and all the negative away from myself. This is a polar molecule. It has ends. The other way to look at it is to decide if you could cut the positives away from the negatives. If you had a real thin knife, you could basically cut the feet off this thing and separate them from the nitrogen. So you could basically run a slice right across there and lop off the feet. Since it has ends, we know that this thing is going to be a polar molecule. We'll do one more together. CF4. Carbon has 4 valence electrons. I've got 4 fluorines at 7 valence electrons each for 32 valence electrons. Halogens prefer to be around the outside, so the carbon's going to go in the middle, the fluorine's around the outside, and I've got enough electrons to give every fluorine an octet of electrons. Now I check the electronegativity on carbon and fluorine. I find out that they're fairly different from one another. So yes, this has polar bonds. Now I have to draw my molecular shape. So this one is again built on the 4 electron positions, this time with the carbon in the middle. So we draw our tetrahedron for our electron shape, put in the atoms where they belong, and this time I'm not going to erase any of those positions because all the positions have an atom at the end. So I don't have to erase anything. The fluorine is more electronegative than the carbon, so the electron cloud in this molecule in every case is shifted toward the fluorine and away from the carbon, leaving the carbon with a partial positive charge. Carbon is black, and we'll use the purple ones to be the fluorine this time. And I don't care which size bonds you use for this. I'm going to use 4 little ones. And sure enough, our molecule kit confirms our choice of tetrahedral here. And with my fluorine being negative and my carbon being positive, I now try to take this thing and point all the negatives away from me and the positive toward me. And what you'll find out is that even though this molecule has polar bonds, the molecule itself doesn't have a positive or negative end. It's got all the negative around the outside, all the positive trapped in the middle. This is a nonpolar molecule, even though it has polar bonds, because we can't find one end that's positive and one end that's negative. Likewise, we can't come up with one straight slice that would cut all the purples away from the blacks. And so the net result here is this molecule is nonpolar, despite the fact that it has polar bonds. So I'm going to give you some time to do the rest of the molecules on here. I cannot stress enough what you can learn from involving either the model kit or the digital model kit. The more you touch and handle the model kits and the more you look at 3D renderings of this, the easier and easier it's going to be. You've got plenty of time. I would encourage you to involve the model kits as you move along and work your way toward deciding polar and nonpolar on all of these various molecules. Okay, the time is yours.